Good evening, guys. Today you're going to have your first, I guess, and only set of video notes on oscillations. This is chapter 14. This has to do with simple harmonic motion. Primarily, we're going to be focusing on springs. We've already kind of talked about springs a lot with regards to energy and such earlier in the year, so this should be a little bit of a review for some of this stuff. So just a couple of definitions first. Oscillatory motion is what we call simple harmonic motion. It's a repeated back and forth movement. Primarily, we denote it that way because it's caused by a restoring force, or some force that's going to try to pull the object back to its equilibrium position. So for most of our practice, we're going to focus on springs, and for right now, it's going to be horizontally moving springs. I'm not going to worry too much about vertical due to time constraints. So remember that when we have a spring that's in equilibrium, there's no force on the object that it's attached to. Only when we pull that spring out or compress it does that restoring force try to bring that object back to its equilibrium position. This is why this value here is a negative, because the restoring force always acts in a direction opposite to the object's displacement. So I have a little graphic here to kind of show that to you guys. If I extend this spring outwards in this direction, we're stretching it. This is the equilibrium, this middle part, sorry. The force of the spring is going to be in the opposite direction as the stretch because it wants to pull this block, this mass, back to this center spot. Same thing with the compression. If I'm going to compress it past equilibrium, well, now all of a sudden the spring force is going to act in a direction opposite of that. So this distance, since it's going past where it started, this distance would be a negative number, so that would make your spring force be positive. I'm just really more concerned with the fact that you understand that concept, whether or not your answers are actually negative or positive, but just know that that force is always going to try to pull it back to equilibrium. So here's a little bit reminder on Hooke's law and Newton's second law. This is Newton's second law, of course, F equals ma. So if I combine those two and I put the spring force in our Hooke's law here for the F, I get that negative kx is equal to ma. So if I want to find the acceleration of the mass or the acceleration of the spring system, I can do so by doing acceleration is equal to the negative kx over m. So in this case, we can see that the acceleration is proportional to the displacement in this case. The farther the spring is stretched or compressed, the greater the acceleration of the object back to equilibrium. So the faster it will go or the slower it will go. So a little bit of a recap on vocab. The first is word is period, which we've already talked about a couple of times with the planets. But the period is the time for one complete oscillation. So that means away and back. So not just away from equilibrium and then back to equilibrium. It would be away from equilibrium and then completely back to the position where it started from. We denote that with a capital T, and it is measured in seconds. Frequency is the number of oscillations per second. We measure that in hertz. So these two suckers are inversely related. You guys probably, hopefully, you remember this from when we talked about waves last year. Let me see if I can't get my pen up and working here. Not in red, though, in white. So we said that frequency is the inverse of period, and period is the inverse of frequency. We talked about that relationship last year. And then amplitude is denoted with a capital A, and it is the maximum distance away from equilibrium. So how far did you stretch that spring out? How far did it compress? This is typically measured in meters, but you can see occasionally it will be in centimeters. So we're going to talk about oscillating springs and kind of the patterns that they make and how we can discuss the position of the oscillation. We're going to use a little bit of trig to do that. So for the position of an oscillator, this is our expression. X is the position that we're trying to find. A is the amplitude, or the maximum distance away from equilibrium. And when we look at this in a second, you're going to see how this, the movement of an oscillator back and forth makes a cosine graph. And so that's essentially what we're doing. Hopefully you guys remember cosine graphs from pre-calc. I think you guys do them pretty extensively in that class. the cosine of omega t plus delta. And this delta represents a phase constant. It really depends whether or not, if the phase constant is even there, but it's where we choose to start our time, where we choose to place t equals 0, depending on how far over that wave pattern will be shifted. That's what this phase constant represents, right, is that shift down the axis. So you guys will see in a little bit how that comes into play. So let's take a look at where did this expression come from? Why do we use a cosine graph to describe the position of an oscillator? So here's a little graphic. I apologize for the blurriness, but the words aren't really important. What's important is that you see the shape. And I said we weren't going to talk very much about vertical springs, but I used a vertical spring for this example because it makes it easier to see. But at maximum compression here, I've pushed the spring upwards. I have a maximum amplitude. So let's just go ahead and draw like a little x-axis happening here. I have an amplitude here from the x-axis upward, and this represents my maximum height. And then I'm going to release that. The spring will extend past equilibrium, and then come back up to equilibrium, and then go back up to the height that I started it at. Again, we're going to assume no dampening effects. Dampening effects would cause this graph to eventually peter out and become a straight line. But we're just going to assume that that's not happening right now. We're going to assume that the energy is staying constant as it vibrates back and forth. So you can kind of see how this is already a cosine shape, especially here. Most of the time whenever we start these graphs, this is our t equals 0 position right here. But sometimes that might not be the case. Sometimes the t equals 0 might be happening here or down here. It just depends. So we're going to do an example where it's not exactly at the top, and you can hopefully see how that all comes together. So let's take a look at the velocity. So we talked about the displacement. So now let's talk about what that means for our velocity. Velocity is the derivative of the position. So we can differentiate our previous expression, which looked like this, and using some calculus rules. Hopefully you guys have done the derivatives of trig functions. If you haven't, it is something that we will talk about when you get here, or when I come back to class. But the rule is that the derivative of cosine is negative sine, and the argument of the function, which is all of this business here, you would differentiate that with respect to time here. So this is omega t plus delta, and so that just becomes omega here outside of the function, since that's the derivative of that. And then, so it becomes your velocity function. And then we can do that one more time to figure our acceleration function. Take the derivative of this, dv dt, to find acceleration. And again, same thing. We're going to take the derivative of our sine function, which is cosine, and this is our result from that. Because again, you're going to take this of the argument here, and that becomes omega. So that comes out here, multiplied by that. Hopefully, maybe you can see that a cosine omega t plus delta is x, is this same expression up here. So that means that a is also equal to negative omega squared times x. Graph-wise, graph-wise, this is kind of what we're looking at. Don't really pay much attention to this graphic up here because I was kind of hoping that the graphic would align with the graph, but it really doesn't. So just kind of focus on the graphs here. Here we have a cosine graph with our maximum amplitude here at the top. And then we can see as the spring vibrates what's happening to the amplitude. The velocity is a sine curve. So it's going to start on the 0 line here because when the object is at maximum amplitude or maximum displacement from equilibrium, it has no velocity. So it's going to gain velocity as it, let me change my ink color real fast. It's going to gain velocity here as the this spring shoots back to equilibrium. Here in this position at the 0 line, this represents equilibrium for our oscillator. And at that position, that's when you should have the maximum velocity. We talked about this with our energy concepts, that as an object swings through equilibrium, whether it's a pendulum or a spring, as it goes through equilibrium, that's when it experiences maximum velocity. And then again, as it goes out here to maximum amplitude just in the other direction, which would be representative of this picture right here, again, you're going to have zero velocity happening at that moment. Acceleration runs the same way as the position, but just the opposite. So when the object is out here extended at its maximum, that's when it has the maximum acceleration, but the direction is going to be a negative acceleration because the force is a negative force, pulling it back to equilibrium. And so vice versa, when it consequently compresses and then wants to extend again, now our acceleration becomes positive as it extends back outward. So over here, I found a graphic with them like superimposed on top of one another. So here the blue line represents our position, what's going on position-wise. The green line represents what's going on velocity-wise, and the red line represents what's going on acceleration-wise. The omega that you guys are seeing in these equations is not really angular velocity, it's really angular frequency, but it means pretty much the exact same thing. It still is a descriptor as to how fast the oscillator is moving, but it just more accurately describes the speed of the vibration back and forth. So your book will speak about angular frequency, but don't let it throw you off. The concept is still the same. Angular frequency is equal to 2 pi over the period. So again, it's radians over seconds. It's the same thing that you guys are used to, but it describes how the rate at which it's making a complete circle. So that means we talked about how frequency is the inverse of period here. So that means that frequency could be equal to omega over 2 pi, because 1 over period would be the inverse of that. So that's what this relationship would be. Or we can say period is equal to 2 pi over omega. All right, period of a spring. We talked about this last year, but I just need to bring it up here. I don't really know how much pendulums are associated with on the APC test. I have to double check, but if we have a pendulum, which I don't think we do, I will review that. The period of a pendulum is very similar, but it depends on length and gravity. But here, for a spring, which is kind of our focus right now, 2 pi square root of m over k. The period and frequency of a spring do not depend on the amplitude. So how far you pull the spring back will not affect the rate at which it vibrates. I guess I shouldn't have said speed, because the fact remains that if you pull it back really far, the acceleration will be greater, but it'll still make the same number of vibrations back and forth. I should say the rate at which it vibrates. That would be a better word instead of speed. So this concept's really important for music, because if your amplitude depended on the sound that you heard, remember with waves and sound, amplitude corresponds to volume. So that would mean that if I played a note really, really loud, then it would sound different than if I didn't. And that would make music pretty much impossible to learn and collaborate with. So energy in oscillators is our next little thing here. Remember, our equation for the potential energy of a spring is U equals 1/2 kx squared. We learned that in a couple of chapters ago. But x, now we have an expression that describes what's going on x-wise, and this is it. And so we can plug that bad boy in and we get this whole mess down here. It's really only going to be important if they ever give you the trig function that describes the wave. If they've given you the displacement here already, or maybe you already know the energy, it's perfectly acceptable to still use this expression. I don't want you guys to think that you have to use this, but I'm just presenting it to you in case you are given angular velocity and phase constant as opposed to an x value. All right, another way to do this is talking about kinetic energy, and it works the same way. Remember our V expression is negative a omega sine omega t, I'm running out of room, plus delta. So we're just going to square the velocity here, and this is what we end up with. So I said that acceleration is negative kx over m. So remember also I said that acceleration is negative omega squared times x. So it's possible that I could kind of combine these two ideas and say that negative kx over m equals negative omega squared x. And then I can kind of cancel that out, cancel that out, cancel that out. And I'm left with this idea, that omega squared equals k over m. So, So if you put that into this expression, it will allow the m's to cancel out, and you're left with a little bit of a, you're left with a little bit of a cleaner way to talk about this. We can say 1/2 k a squared omega squared sine squared omega 2 plus delta. Ooh, that's a mouthful. Okay, these are super long, but in essence what I'm doing here is showing you guys the energy of an oscillator is what you get when you add your kinetic plus your potential. That'll give you your total energy. That's the same way it's always been. It's just how it is. So if I were to add those two expressions together, this is what I would condense it down to. The total energy in an oscillator is proportional to the amplitude of the oscillation. So kind of makes sense to what I was talking about before. The farther you extend your spring, the faster it's going to move, which increases the energy of the system. And remember, this works the same as we learned it before. At maximum displacement, all of the energy is potential, and then as it moves towards equilibrium, it's going to lose potential and gain kinetic. Okay, welcome to the problem-solving section of this video. We're going to do a little bit of work with our frequency, period, all of that stuff, cosine, sine business, and then we're going to do an example with energy. So the first thing we're going to do is look at an example where we have a 2 kilogram object, we're going to say, is attached to a spring, and the spring constant is 196 newtons per meter. And we're going to pull that object out to a distance of 5 centimeters from the equilibrium point, and it's released at t equals 0 seconds. So the very first thing we want to do here is we want to find the angular frequency, the frequency, and then the period. And then the second part of this problem is to find x as a function of time, is what we want to write an equation for. So here we go. Part A. Now here, the period, we've got mass, we've got our k. We can figure out what the period of our spring is, because period is 2 pi square root of m over k. So this is 2 pi square root 2 over 196, and when we plug all of that business in, we get 0.63 seconds for our period. Now, to find the frequency, all I have to do is take the inverse of that number, so 1 over 0.63. That gives me a frequency of about 1.5 hertz. So, 0.63, 1.5. All right, the next part of this problem is solving for our angular frequency. And angular frequency and period are related through that previous expression I showed you. 2 pi over omega. So again, we can just plug and chug from here, and we solve 0.63, 6.28, and we find our angular velocity. I'm sorry, not angular velocity, angular frequency to be about 9.9 radians per second. All right, the last part of this expression, or the last part of this problem, is to find our position equation as a function of time. Position as a function of time for an oscillator uses this general equation format. So our amplitude in this case, since we pulled the spring out to 5 centimeters and released it, our amplitude is 5 centimeters. That's the maximum distance away from equilibrium. So since we've chosen that to be the beginning position, we don't have a phase constant, right? If we had chosen the beginning position maybe to be somewhere in the middle of the oscillation, then perhaps this phase constant would be important, but right now it's not. So x equals 5 centimeters. We'll put this in centimeters so everyone knows it's centimeters. Cosine 9.9 times time. And that's our expression for the position of this oscillator. We could go a little bit further and do some work with the velocity here. So what is the maximum speed of the object? Let's look at that. Let's do a same object, same position expression, but now we're going to focus on what is the maximum speed of the object. So remember that the maximum speed is going to occur at this particular moment, right? When the sign of the function here is 1, that's when we're going to have our maximum velocity. But remember, there's no phase constant for this particular guy, and sine omega t is 1, so that just really cancels out. So our Vmax occurs when we have our angular frequency times our amplitude. And in this case, our angular frequency we found in the previous problem was 9.9, and our amplitude is 5. So at that moment, our velocity, sorry, this is 5 centimeters too, ends up being 49.5 centimeters per second is our maximum velocity at that particular moment. So let's look at what happens when you have an object 2 kilograms and a spring constant of 40. And the object is moving at 25 centimeters per second when it's at equilibrium. So at equilibrium. And let's say, what is the total energy of the object? So I don't want you guys to freak out and think that you automatically have to use those sine and cosine functions. You really don't. We can still use our traditional energy ideas, but I presented those to you guys in case they're giving you values like angular velocity and, angular frequency and all of that. But the first part here is, what is the total energy of the object? So we talked about how the total energy of the object is going to be, in this case, they've told us a special condition. They've told us that the thing is going 25 centimeters per second, at equilibrium. And remember that as the object goes through equilibrium, all of its energy at equilibrium is kinetic. So kinetic energy, in this case, is, my thing's not working very well right now. Kinetic energy, all of the energy here is kinetic. So when we solve for the total energy, what we're going to solve for is the kinetic energy at equilibrium, and then that'll tell us our total. So we've got 1/2 mv squared. We're going to place in 2 kilograms for our mass, and we're going to convert this into meters per second. So that's going to be 0.25 meters per second. Let's cross off this C. And then we're going to square that, and we're going to get our total energy for our object to be 0.0625. Sorry, my thing's acting really weird. I have to use my mouse right now, so this is going to look pretty janky. Part B asks, what is the amplitude of the motion? And so remember that total energy is 1/2 Ka squared, where A is your amplitude. So we have our total energy to be 0.0625, and we're going to plug that in and divide it by 1/2 and then divide it by our k, which in this case is 40. And then we're going to square root that, and we get our amplitude of our spring. And the amplitude of our spring ends up being about 5.6 centimeters, give or take. All right. The only thing that is really left to talk about in this section is a little bit about vertical springs and a little bit about pendulums, but we've already discussed vertical springs a little bit when we talked about energy and forces. So that doesn't change too terribly much. I mentioned the pendulum thing earlier in the PowerPoint, but keep that equation in mind because there are a couple of book problems that deal with it, but in case you didn't write it down before, it's the period of a pendulum. It's 2 pi square root of L over G. Where L is the length of the pendulum and G is gravity. So of course the period of a pendulum does not depend on the mass of the pendulum bob, but mass is a factor when you're figuring out the period of a spring. So remember those two things in general. And that is all I had to point out for you guys, and I will see y'all when I get back. Bring your books on Thursday and Friday.